In response to the exhaustion of IPv4 network addresses in the early 1990s, the Internet Engineering Task Force, IETF, initiated the development of a replacement protocol, which is now known as IPv6. To gain a deeper understanding of IPv6, I recommend adding Rick Graziani's IPv6 Fundamentals to your study resources. His book serves as a definitive source for everything related to IPv6. IPv6 addresses the need for a vast supply of IP addresses and improved mobility, surpassing the limitations of private addressing and network address translation, NAT. IPv6 offers several benefits and features including 1. Extended address space. IPv6 provides a 128-bit address space, accommodating approximately 340 undecillion addresses. 2. Stateless address auto-configuration. IPv6 enables host devices to generate their own routable IPv6 addresses. DHCPv6 can also be used for stateful configuration. 3. Elimination of NAT-PAT. With IPv6, address depletion is no longer a concern, rendering NAT-PAT unnecessary. However, NAT64 plays a role in maintaining backward compatibility with IPv4. 4. Simpler header. IPv6 employs a simpler header compared to IPv4, resulting in improved routing efficiency, absence of broadcast storms, no checksum processing requirement, and more efficient extension header mechanisms. 5. Mobility and security. IPv6 integrates mobility and security features, allowing mobile devices to move without disruption to network connections. IPsec is enabled on every IPv6 node, enhancing overall network security. 6. Transition strategies. IPv6 can be implemented alongside existing IPv4 capabilities through dual-stack configuration or tunneling. Dual-stack involves configuring both IPv4 and IPv6 on network devices, while tunneling enables IPv6 packets to be transported over IPv4 networks. This is a comparison between IPv4 and IPv6. IPv6 utilizes 128-bit addresses represented in 64-bit words, while IPv4 uses 32-bit words. IPv6 introduces various address types to accommodate the diverse addressing requirements of modern networks. Let's delve into each IPv6 address type in more detail, along with detailed examples. Unicast addresses identify a unique interface on an IPv6 device. A packet sent to a unicast address is intended for delivery to a specific interface associated with that address. IPv6 defines several types of unicast addresses, including global unicast, link local, and unique local addresses. Global unicast address. Global unicast addresses are globally routable on the IPv6 Internet and are equivalent to public IPv4 addresses. They allow devices to connect to the global Internet and communicate across different networks. Global unicast addresses have a hierarchical structure consisting of a global routing prefix, subnet ID, and interface ID. Link local address. Link local addresses are used for communication within a single link or network segment. They are automatically generated by devices when no global unicast address is available or necessary. Link local addresses have a well-known prefix, F80:10, and are unique within the local network. Link local addresses are configured in one of three ways. Dynamically using EUI64, using a randomly generated interface ID, statically entering the link local address manually. Unique local address. Unique local addresses, ULA, provide private addressing similar to IPv4 private addresses, for example 192.168.0.0/16. They are designed for local network communication within an organization or site. ULAs have a global ID randomly generated to ensure uniqueness within a global scope. Multicast address. Multicast addresses identify a group of devices that belong to the same multicast group. A packet sent to a multicast address is delivered to all devices subscribed to that group. IPv6 multicast addresses have the prefix F00:8. Assigned multicast addresses. Assigned multicast addresses are used in context with specific protocols. Two common IPv6 assigned multicast groups include the following: FF02:1 all nodes multicast group. This is a multicast group that all IPv6 enabled devices join. As with a broadcast in IPv4, all IPv6 interfaces on the link process packets sent to this address. For example, a router sending an ICMPv6 router advertisement, RA, uses the all nodes FF02:1 address. IPv6-enabled devices can then use the RA information to learn the link's address information, such as prefix, prefix length, and default gateway. FF02:2, all routers multicast group. This is a multicast group that all IPv6 routers join. A router becomes a member of this group when it is enabled as an IPv6 router with the IPv6 Unicast Routing Global Configuration command. A packet sent to this group is received and processed by all IPv6 routers on the link or network. For example, IPv6-enabled devices send ICMPv6 router solicitation (RS) messages to the all routers multicast address requesting an RA message. Solicited node multicast is a mechanism used in IPv6 to perform address resolution and duplicate address detection. It involves the use of special multicast addresses called solicited node multicast addresses. In IPv6, each device has a unique unicast address assigned to its interface. In addition to this unicast address, the device also has a corresponding solicited node multicast address. This multicast address is automatically generated by combining the device's unicast address with a specific prefix. The solicited node multicast address serves two important purposes. 1. Address resolution, similar to Address Resolution Protocol, ARP, in IPv4. Address resolution in IPv6 allows a device to determine the link layer address, such as MAC address, of another device on the same network. To perform address resolution, the requesting device sends a neighbor solicitation (NS) message to the solicited node multicast address associated with the target device's IPv6 address. By sending the NS message to the multicast address, the requesting device ensures that the message reaches all devices on the local network that have the same solicited node multicast address. The target device, identified by its IPv6 address, then responds with a neighbor advertisement (NA) message containing its link layer address. 2. Duplicate address detection (DAD). Duplicate address detection is a process that ensures the uniqueness of an IPv6 unicast address on a network. When a device is assigned an IPv6 address, it needs to verify that no other device on the network is already using the same address. To perform DAD, the device sends an NS message to its own solicited node multicast address. If any other device responds to this NS message, it indicates that there is a duplicate address conflict on the network. The solicited node multicast address consists of two parts: the prefix FF02:0:0:0:0:1:FF00:1/104 and the last 24 bits of the corresponding unicast address. This combination ensures that the solicited node multicast address is unique and corresponds to a specific unicast address. By using solicited node multicast addresses, devices in an IPv6 network can efficiently resolve the link layer addresses of other devices and detect duplicate addresses, enabling proper communication and addressing on the network. Anycast addresses. Anycast addresses identify a group of devices, and the packet is delivered to the nearest device in the group. Devices with the same Anycast address advertise the same address, and the routing infrastructure determines the closest one. Anycast addresses are typically used for load balancing or selecting the nearest service instance. Example: suppose multiple servers provide the same service, and they all advertise the Anycast address 2001:0DB8:1234:5678:/64. When a client sends a packet to this Anycast address, it is routed to the server that is topologically nearest, providing efficient and localized service delivery. Understanding these IPv6 address types enables network administrators to effectively design networks, plan addressing schemes, and troubleshoot connectivity. By leveraging the unique characteristics of each address type, organizations can ensure seamless communication and efficient utilization of IPv6 addressing resources. Representing the IPv6 address. Conventions are used to write IPv6 addresses, and two rules help shorten the configuration of an IPv6 address. Rule 1. Omit leading zeros in any hexstet. Leading zeros within each hexstet can be omitted for brevity. For example, 0DF8 can be written as DF8, or 00F2 can be written as F2. Rule 2. Omit all 0s hexstets. Consecutive hexstets of all zeros can be represented by a double colon, but this abbreviation can only be used once in an address. To clarify these conventions, let's examine an example IPv6 address. In this address, there are two instances where one or more hexdets have 4 zeros each. Two valid abbreviations using the double colon notation can be used. The second and third hexdets preceding 0001 are replaced with a double colon. The fifth, sixth, and seventh hexdets are replaced with a double colon. Note that the double colon abbreviation cannot be used more than once, as it would create ambiguity. Therefore, an address like FE00:1:56 would not be valid. When it comes to writing IPv6 prefixes, which represent a range or block of consecutive IPv6 addresses, the following conventions apply. 1. The prefix length determines the number of significant bits in the prefix. 2. Bits after the prefix length are set to binary zeros. 3. The prefix can be abbreviated using the same rules as for IPv6 addresses. 4. If the prefix length is not a multiple of 16, the remaining bits in the last hexdet are specified explicitly. This is the corresponding prefix. This is the abbreviated form of this prefix. If the prefix length is not on a hexdet boundary, the value for the entire hexdet is written explicitly. For instance, if the prefix length is /56, the rest of the fourth hexdet is written as 2000:1234:5678:9, a 00:/56. Here's a summary of key points for writing IPv6 prefixes. The prefix value is the same as the IP addresses in the group for the first number of bits defined by the prefix length. Bits beyond the prefix length are set to binary zeros. The prefix can be abbreviated using the rules for IPv6 addresses. If the prefix length is not on a hexdet boundary, the value for the entire hexdet is specified explicitly. This table provides several sample prefixes, their formats, and a brief explanation. Static IPv6 addressing involves configuring a router to use EUI64, Extended Unique Identifier, addressing. EUI64 configuration is designed to simplify the auto-configuration of IP addresses by leveraging the MAC address of a network card. In IPv6, the second half of the address is known as the interface ID, which can be set to any value as long as it remains unique within the subnet. However, the interface ID was specifically designed to accommodate auto-configuration using the MAC address. MAC addresses consist of 6 bytes or 48 bits. To create a 64-bit interface ID, IPv6 divides the MAC address into two 3-byte halves. It then inserts the hexadecimal value FFFE between the halves and sets the 7th bit of the first byte to binary 1. This results in the formation of the interface ID field, following the EUI64 format. To better understand the EUI64 format, consider the following example. In this case, the MAC address is divided into two 3-byte halves, 1234:56 and 78:AB:CD. The hexadecimal value FFFE is inserted between the halves, resulting in 1234:56 FF:FE78:ABCD. Stateless address. Auto-configuration, SLAC, is one of the methods used for dynamic configuration of IPv6 addresses. With SLAC, a host learns the /64 prefix dynamically through the IPv6 Neighbor Discovery Protocol, NDP, and calculates the rest of its address using the EUI64 method. This process eliminates the need for manual configuration and a DHCPv6 server. SLAC operates by leveraging the EUI64 process and NDP. When a host and a router configured with the IPv6 Unicast routing command interact, SLAC is initiated. The router sends NDP messages to the host, which allows the host to determine its global unicast address without manual intervention. By combining the EUI64 method with NDP, SLAC enables devices to obtain their complete global unicast address automatically, eliminating the need for manual configuration or a DHCPv6 server. The use of SLAC simplifies the process of assigning IPv6 addresses to devices and enhances the efficiency of network configuration and management. Migration to IPv6. Two primary strategies for transitioning to IPv6 are dual stacking and tunneling. Dual stacking involves implementing and connecting to both IPv4 and IPv6 networks simultaneously, while tunneling encapsulates IPv6 packets within IPv4 for transport over IPv4-only networks. Dual stacking is recommended where possible, while tunneling is used when necessary. It is important to keep in mind that the transition to IPv6 may take a significant amount of time, so dual stacking is the preferred method for now. By studying IPv6 addressing, its benefits, and various implementation methods, you will gain a comprehensive understanding of this protocol and its role in the future of networking. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.